Hello, Year 12. Here we are in our third video about circular motion. It's called Centripetal Force. Now, we've already seen that for an object to move in a circle, it must be accelerating. And for something to accelerate, there must be a resultant force. And we call this resultant force that acts towards the centre of the circle the centripetal force. Now, when you see our centripetal force, we can see it's acting towards the centre of the circle. It's always perpendicular to the velocity at any one instant. This means there is no motion in the direction of the force. Therefore, no work is done. Remember, work done is force times distance moved in the direction of the force. And seeing it's not, no work is done. Now, work also causes an energy transfer. So our ball, our object, going round in a circle, does not gain any energy, either kinetic or potential. It doesn't increase in linear velocity, and it doesn't change orbital distance. Okay, so it doesn't change kinetic energies, it doesn't change in potential energies. So when a resultant force acts, resultant force from Newton's second law is equal to mass times acceleration. And we saw in the previous video that acceleration is equal to v squared over r, and therefore centripetal force equation is mv squared over r, and also mr omega squared. Okay, for the same reasons, remember r omega squared was the second formula which had centripetal acceleration. Now, there are several scenarios we'll be going through that looks at how a centripetal force works. You got to remember, a centripetal force is not a new force. It's a force that's acting. It doesn't just happen to be an extra one that's created. A force there, or a component of a force, acts as the centripetal force. It is the force that makes it go round in a circle. For instance, with the hammer throwing, the tension in the rope attached to the hammer. For a car, it'll be friction acting towards the centre of the circle. For a planet, it would be gravity. And in this situation of the roller coaster, it would be its weight minus the reaction force in that scenario. Okay, but we're going to look at loop-the-loops a little bit later, and vertical circles, and see the effect of different positions while moving in a circle that could affect the size of the force or the components of the forces involved. Now, the first scenario is the conical pendulum. So, situation like this, just got a ball on the string, there's our mass, and it's moving round in a circle. Now, as you can see from the diagram, we've got tension in the string, they're using the symbol F, and therefore the component towards the centre, F sine theta, is the size of the centripetal force towards the centre of the circle. That is the size of the force accelerating that ball towards the centre. And then we can apply this general equation, mv squared over r. Okay, so if we were doing some mathematics with it, if we know the mass of the ball, the velocity of the ball, and the radius of that circle, and the angle it is at, we could work out the size of the tension in the string. Okay, nothing to do really with the circular motion, but we can see that the weight mg must be balanced by the component of the tension in the vertical direction, F cos theta. Now, as I increase the speed of this, we can see the angle theta is getting larger. Okay, so we need the tension in the string will be going up as we're needing a greater centripetal force towards the centre. Okay, and you can actually never get it perfectly horizontal, no matter how fast I go. Okay, and the reason for that is we always need a bit of component to balance that weight. So the angle might get very, very large, but we always need a bit of that F cos theta to balance the weight of the ball. Second scenario is a car going round a bend. Now, normally, going round a road that was just flat on the ground, the component would just be caused by the friction of the road. So F would equal mv squared r, where F would be the size of the force of friction. But you can get what we call a camber on the road, and particularly high-speed corners and that, they tend to use cambers, okay, to help make the road a little bit safer. So you can actually go a little bit faster around it before you start skidding off. Now, sometimes you'll see, if you're learning to drive, you might see some roads with corners that give you a warning for an adverse camber, and that is where the slope is the opposite direction, and therefore the reaction is giving you a component away from the center, and therefore you can have smaller amounts of friction. So what you're just going to be able to do is to resolve your components into the directions towards the center. So you can see we've got on this case the normal reaction. Okay, there'll be individual ones at the wheels, but the total would be r, and it would be r sine theta towards the center of the circle. But there'd also be a component from the friction of the tires. It doesn't show that on the diagram. Fr cos theta towards the center of the circle. Again, adding those forces up, the total of those forces, they're both contributing to centripetal force, must equal the general centripetal force equation, mv squared over r, or mr omega squared. Vertical circle. So when we've got an object going like that. Now, if we look at different situations within the vertical circle, if we think about position 1 at the bottom, we have got T1 acting towards the center, but you've got the weight of the object acting in the opposite direction away from the center. Therefore, the resultant of those, T1 minus mg, produces your resultant force towards the center of the circle. So T1 minus mg equals mv squared over r. If you look at T2, mg is perpendicular to the direction of T2, so we can't do a resultant force towards the center in that situation, but therefore T2 in that position there is the only force that is contributing towards the centripetal force. And that's exactly the same for in the opposite side, because we've also labelled that T2 on the diagram. When you get to the top position, the weight of the ball is acting downwards and the tension is acting downwards. So both of these are contributing towards the centripetal force. So T3 plus mg equals mv squared over r. Now, if in all the situations it's going at the same speed all the time, your object going round in a circle, mv squared over r is always the same value. Mg is always the same value. So the values of T1, T2 and T3 are what are changing as it's moving around. T1, when it's there at the bottom, is going to be a larger number than T3. If you can just imagine, if you're doing a vertical circle, if you're not going fast enough, the string gets limp at the top and it'll fall down. So tension reduces in here compared to where it increases at its maximum when it's at the bottom. So just got to take these ideas into consideration when doing your calculations. A loop-the-loop on a roller coaster is very, very similar. When it's at the top of the track, you've got the reaction force of the rail and the train acting downwards, as well as the weight of the object. So r plus mg equals mv squared over r. And at the bottom, r minus mg equals mv squared over r, because you've got the reaction upwards, mg downwards, but it's always towards the center of the circle, the resultant, so r is going to be bigger than the weight when it's at the bottom of the circle. Okay, and that's why in certain scenarios, you know, if you think about how you feel in your seat when you're in a roller coaster loop-the-loop, okay, r gets a bit less at the highest point. The reaction force, you feel like you're going to fall out your seat, you're not being pushed in your seat. At the bottom, r is very, very big. Okay, you feel like you're being pushed right into your seat. Okay, so you can actually feel the effects of these if you are on a roller coaster, if you're that sort of person who goes on them. So again, just remember to take account of the resultant force. You've got to look for all the forces that are acting towards the center of the circle or away from it or in those directions. If they're perpendicular, they can be ignored. Even something like a humpback bridge, a car going over a bridge. Okay, the centripetal force at the top will be mg minus n, the reaction force in this case. Okay, it's moving over basically a circle. And again, that's why you can tend to feel like you're coming out of your seat in those scenarios. And it's just a case of getting used to them and practicing, and you'll be fine. So, in summary, what you need to know is a centripetal force acts towards the center of the circle to cause the centripetal acceleration. It is a resultant caused by other forces acting towards the center of the circle. It isn't an extra force that just appears. Okay, the other forces acting make up that resultant force, that centripetal force. And the two equations that you will need to use, F equals mv squared over r and F equals mr omega squared. Now this idea is really, really important, okay? We're going to be building up on this when it comes to the fields topic in particular, when we've got gravity and Newton's law of gravitation causing things to go around in a circle and Kepler's laws. It's also when, say, electrons orbiting nuclei, we use these ideas with fields, and so they can get really quite complicated. So we've got to get these basics sorted over these next few weeks before we hit the hard stuff. Okay, this is an introduction. So we've got some examples. So example one is just looking at a car going round a bend. So what is the centripetal force needed from friction to keep a car at mass 1,000 kilograms following a curve of radius 50 meters at 18 meters per second? So we know the car's mass, we know the radius of the circle, we know the velocity, and this is the tangential velocity, the velocity the car is going. So F equals mv squared over r, we stick in our numbers, so it's 1,000 times 18 squared over the radius of the circle, 50, and we get 6,480 newtons. Okay, so that one, just working out F, we've just got to plug our numbers in. Let's look at example 2. A roller coaster has a vertical loop of radius 12 meters. The cars go around at 4 meters per second. Calculate the centripetal force required for a passenger of mass 60 kilograms and the contact force on the passenger at the top and the bottom of the loop. Okay, so that is R, in other words. So we know little r is 12 meters, the radius. We know v, the velocity of the car, is 14 meters per second. So we can work out what the centripetal force is for a person of 60 kilograms. Okay, because you're going around in the loop as well as the whole train. So you can just look at an individual person, make them the system. So F equals mv squared over r. So it's 60 times 14 squared over 12. It equals 980 newtons. Now, if we're looking at the contact force at the top, so providing that centripetal force is R plus mg. Now we know that the centripetal force is 980 newtons, so R plus mg must equal 980 newtons. It is the mv squared over r part of the formula showed at the top. Therefore, R must equal 980 minus 60 times 9.81 mg, weight, equals 391 newtons. At the bottom, R minus mg equals 980 newtons, just like before. So R equals 980 plus mg, so it's 980 plus 60 times 9.81, which is 1,569 newtons. Okay, and it's because of those difference in those reaction forces on why at the very top of the loop you feel light in your seat, you feel like you're going to fall out, that's part of the thrill. And at the bottom you feel like you're being squished into your seat. Okay, because the force you're put on your seat, the seat is putting back on you. You feel like you're being squished in there. Example 3. What is the minimum speed